Hi everybody, welcome to my talk for FSE150. The talk title is Empowering Artists in the Age of 3D GenAI. My name is Pavan Turaga. I am a professor and founding director of the Game School at ASU. The name Game School stands for Games, Arts, Media, and Engineering. So we are a really hybrid school that talks about how technology impacts the media industries very broadly with a special focus on gaming. And as you may have seen, interest in 3D asset creation in 3D games is on the upswing. So this talk is really about how AI tools come into play when we talk about 3D asset creation and 3D content creation, and what the limits are, what the opportunities are, and how you can have some fun in this space. I'm also a designated faculty in the Joy of Living theme area for the FSC Grand Challenge Scholars Program, and hopefully some of this content will help you think about projects you can do in that theme area. So the first slide talks about how the 3D market is actually expanding. People almost always underappreciate the coming impact of 3D. We think about 3D and associate it very directly with things like virtual reality and augmented reality, but there is a lot more beyond that. 3D asset creation and 3D content creation has many industrial applications. 3D digitization is very big in the manufacturing industry, in construction, and all kinds of areas where walkthroughs may be needed without necessarily having to build it out in full scale. So 3D asset creation is significantly impacting many industries beyond just gaming. But for us, for the purposes of this talk, we are going to be focusing on gaming. And the bottom graphic shows you how the market in gaming is also steadily increasing and is expected to increase fairly linearly over the next decade. So if you're interested in 3D content creation or gaming or virtual reality or even adjacent areas like 3D digitization, 3D scanning, it's going to be very important to keep abreast of the impact of AI in this area, and we'll talk about that in a minute. So I'm sure everyone has heard of generative AI, which is the biggest game-changing name in the AI world that everyone is grappling with. GenAI stands for Generative Artificial Intelligence, which is a way in which we train AI models to create full outputs of media, including text to image, text to video, text to 3D, and even text to full-on, feature-length films are being talked about. Text to full-on games is going to come about in the next year or two. So a lot of stuff is going to change in how media content is created through AI tools. But there are limitations. For example, I'm going to show you a bunch of rendered outputs from some standard text to 3D generators that are considered popular at this point of time. And these are all just text prompt to 3D generators. So we've given it inputs like, oh, get me a picture of a vulture, for example, in 3D. And it creates things that pass off as appropriate and good looking when seen under the right perspective. But when you start rotating these objects and look at different views, it starts revealing some inconsistencies. For example, look at this ostrich. It looks like it's got 3 heads. As you spin around, you're always seeing a head. You never actually see the back of the ostrich's head. If you look at this little dog on the bottom, it also looks like it has 2 heads, by the way. When it turns around, you see another head. But it also seems to be getting the number of paws wrong. So there's going to be errors like this. Some of them tend to be very obvious, some of them tend to be very subtle, but by and large, what we're finding with 3D generative tools is that they do a decent job, which looks like a good model, a good 3D model was generated at first glance, but when you start probing at it from a very detailed perspective, it starts showing inconsistencies. Some of the other inconsistencies we see include things like the holes in the shape. Sometimes the holes are not even fully rendered. There are gaps and holes, and the topology of the shape is not proper. So we'll talk about 2 kinds of technical terms in this talk, topology and geometry. And I'll get to that in a minute. But geometry generally refers to the full shape, meaning geometry refers to how the distances on the shape are being rendered. And topology refers to connectivity. So I'll get to that in a bit. But I also want to contrast how AI works in comparison to how classical content creation works. If you're an engineer, you might not see this kind of a pipeline in practice. But if you're in the media side, if you're a filmmaker, if you're a game producer, if you're a theater person, whoever, anyone who produces media knows of a kind of a prototypical pipeline in media production. There is a pre-production stage, there is a production stage and there is a post-production stage. And actually, this phase is also playing out while I'm talking right now. So we are right now in the production phase of my presentation. And right after I finish, there's going to be a post-production phase where there will be a lot of editing done and a lot of cleaning up done. So this is very standard in media production, that there is a pre-production stage where people think about idea and story and they sketch things, and there is something called pre-visualization, storyboarding. Depending upon which industry you're in, you use different words, but it's very analog. There is no digital component really. And then the production is where you start assembling things. You start making, if you're talking of film, you start taking little shots at a time, and then you start assembling them in post-production. Or if it's a game, the production looks like, well, I need someone to build my background scene. I need someone to build the sound in the game. I need someone to build my individual 3D models that are in the game. Someone needs to think about the game mechanics and code up the rules of the game. And then all of that assembly then comes back into post-production. So when you look at this, this is how the media industry thinks about content creation. This is very different than how AI tools are doing content creation. AI tools are still very much trying to solve text prompt to full output kind of an approach. And when you look at this complexity in production, it reveals to you that, well, AI may have a lot of catching up to do. But it sounds like still, even without this kind of detail, now this is very professional like. This pipeline that you're seeing is very professional. For more less professional and more, amateurish, that's a negative connotation, but it's for people who are enthusiasts, who want to create a little quick game in 3 hours and, just get it out. Yes, AI tools are still very impactful, but for AAA game studios, if you want to build a game like Mortal Kombat, no, you're not going to be able to do that with an AI tool in 3 hours. There's going to be months and months of work. So that spectrum is where, you have to have some appreciation of where AI tools might actually help and where they might have some limits. So there is the other technical side of it, which is AI model development has many intrinsic bottlenecks that have to do with the amount of data you have to train it. In this picture, I'm showing you a visualization of the disparity in the size of data sets available to train AI models in 3D versus what I'm calling 2D or image data sets. So on the right, this big circle is the size roughly of the image data sets that are available on the internet. So 10 to the power 10, which is like 10 billion. That's the scale of the pictures that are available on the internet for companies like OpenAI to scrape and build image generative models, which are fairly robust at this point of time. And even in that space, actually, even image generation, despite having this much data, people are still finding that AI image generators can make mistakes, and some very classic examples include they get the number of fingers wrong for some reason, and then you can attribute that to the notion that maybe there aren't enough pictures on the internet with all fingers showing for all people, so it kind of fudges things a little bit. But 10 billion images is the scale of the image data set that is available, and things seem to be robust enough in that area. By contrast, the largest publicly available 3D data sets is order of 10 to the power 7, which is about 10 million. So it's really 1,000, a factor of 1,000 smaller. And these two circles are trying to give you that visualization of what 1,000 times smaller means. So AI model development for 3D is going to be bottlenecked for the foreseeable future because of lack of large training data sets. But as an engineer who wants to do AI modeling, 3D modeling is particularly timely because when you have these constraints that the data sets are not large enough and there are these consistency problems you're looking at, there's a lot of engineering that can actually happen to help push the field forward rather than rely purely on brute force data. So when you don't have that kind of data, the types of techniques people tend to use tend to be more mathematical. We try and start to define what do we really mean by the geometry of a shape or the topology of a shape. We try to mathematically define these things. And if we have good definitions and if we have good control signals, so to speak, so I'll talk about areas where we may be able to create variations over one high quality 3D shape, but with a small model with some interesting definitions of geometry and topology. So we can create variations on existing high quality shapes without needing billions of data sets. So that's where some of the engineering techniques come in. So I'll move on to what we are doing in that respect. So this is an example of an AI generative model that we have been developing in my lab. The name of my lab is called the Geometric Media Lab, very aptly named. We've been in business for at least 15 years now, and we work on geometric techniques, very broadly construed. And with the rise of GenAI, for us, geometric techniques as applied to 3D has become very compelling right now. But we talk about geometry in a number of different ways, including high-dimensional geometric constraints, but also just good old-fashioned 3D geometry. So the example you're seeing here is the following. What we're seeing here is that we assume that we have access to an input reference shape that is probably made by a 3D art modeler or a 3D artist. And we are trying to create a variation on this shape driven by a text prompt. So the text prompt might look like this: a zoomed out DSLR photo. I mean, the word photo sounds like 2D, but it also works for 3D. A zoomed out DSLR model, let's say, of a ceramic lion. Now, the key part is I want a ceramic lion. So the adjective is ceramic, and there's not going to be enough images out on the internet that help the AI model learn what ceramic means and what that combination means, the ceramic lion means. So we are trying to help it along the way by asking an artist, for example, in this case, to provide a reference 3D shape that may be more commonly and easily available. For example, a reference 3D lion is probably commonly available. So get me at least that bit. And then the text prompt is processed by standard text processing modules, which are common in machine learning at this point of time. The 3D model is processed through interesting methods like rendering it from multiple different angles to create two-dimensional representations, including depth maps and edge maps and so on and so forth. So all these things create what we call a weak loose constraint for our model to compare against. We are not trying to get the same lion as provided by the artist, but we're trying to create a little matching constraint that, yeah, it's a ceramic lion. We don't really know what it looks like, but at least it should have a head, a tail, 4 legs attached in roughly this layout. So when we talk about layout and attachment and connection, what we are really talking about is topology. So that's the other keyword. So we're trying to get our AI model to try to understand the topology of what a lion may be, and then use that as a weak constraint to create this ceramic lion model we are going after. So some of the technical details include, rendering the high fidelity model from multiple angles, and then have a 3D generator process this text prompt and get something the best it can do, and then we refine it. We go back and refine it, and we do this matching between, this is the high quality 3D edge map, so to speak, and this is the ceramic lion's edge map, and we're trying to make sure that they are aligned roughly, at least topologically they are aligned, and we do this iteratively, and then the hope is AI models benefit by that kind of guidance. So this is a very clear example. So some of the models we are putting out are very clearly in the realm of creating more control and more interpretability, especially if you're a 3D artist. We think that there is a space for AI modeling techniques to move in that direction, where there is a clear input that comes from an artist. That's not just a text prompt. And the more you give that kind of control to an artist, the more you amplify their work. I mean, it's going to take probably hours and hours of work for one artist to make a lion, and then a ceramic lion, and then, I don't know, a pink lion. So rather than have to do the same thing 100 times, could you do it one time and use AI models to make variations on it? So that's the kind of model we are proposing here. And we find that this actually works, and this actually helps. So here is some very extreme examples of the types of things that we can do. So the top row shows an example. Again, we are saying a DSLR photo of a ceramic lion, but the artist provided control is not even a lion, it's a horse. And for us, it's fine, because the key mathematical concept that's driving the guidance part is not that it's a horse or a lion, but it's the connectivity, as I mentioned, the topology, that it has 4 legs, it's got a head, it's got a tail. So as long as you give it a shape that has the same topology, we are fine with it. And then this is the output. So it's still, has 4 legs, a tail, a head, but it's preserving that text prompt. And the horse is just there as a weak guidance to help the model get the right topology. Similarly, on the bottom, high quality photo of a furry dog. The control is actually a cat. Once again, the idea is the model only needs the general topology of that shape, and we still get the needed dog 3D model. These are very good examples of the idea that I'm illustrating. That is, we are providing more controls to 3D artists and help them make variations on shapes that they may already have made, and they may not have the time to make every little variation that a client asks for example. The other extreme example that we tried is, well, what if you're not a high quality 3D artist? You can't even make that one horse. What can you do then? So what we find is, yes, take the text prompt, pass it to any of the existing quote-unquote bad 3D GenAI models, and there's plenty of them. So take your text prompt and put it into any of the existing publicly available 3D generators. You will get something, okay? But you will get inconsistent results, right? You'll get, things with multiple heads, or like I mentioned earlier, the number of paws might be wrong, there might be holes, this and that. That's okay, take it. And use this as guidance in the same approach that I mentioned, and we are still finding that the final output, even when they're guided by bad quality 3D, is still good. It's not as good, I think, as the one that's guided by a 3D artist, but it's still reasonable. Same thing, ceramic lion. Once again, we use an existing 3D generator, which is quote-unquote bad, which means it's got multiple lion heads popping up. But then we use this not as a hard constraint, it's a weak constraint, and we still get a good ceramic lion out of that. So this is the way we are evolving the field. We are publishing some of these results in major conferences in AI. One of the ways we quantify whether we are doing well or not in 3D is to measure what is called the Janus rate. The Janus is a classic sculpture from probably Greek or Roman architecture, which has 3 heads or 4 heads on facing multiple sides. If you are into Hindu mythology, you might call it the Brahma rate, 4 heads pointing in 4 different directions. So we actually look at the generations that we create, and we manually go into each one, and we validate it visually to see if we got multiple heads somehow in there. So a reduction in the multiple heads rate is good, and that multiple heads rate is called the Janus rate. So these are all the Janus rates for existing 3D models, and this is something we published earlier in spring 2025, and we were doing much better than standard 3D models out there. But our assumption there was that there is some high quality topologically equivalent shape guiding all this, so that helped in reducing that multiple phase effect. We are advancing this idea into a few new directions. DCOM Dreamer is a very recent body of work we are advancing. It's not published yet, it's under review at one of our conferences, where we are going from one asset at a time to full scenes at a time. And I would use the word scene a little vaguely here, in the sense of when I say a scene, we are saying a scene that may have multiple objects in a particular layout, that A is on B, behind C, that kind of prompt. For example, we are looking at processing prompts like this, which is in vertical orientation here, 2 macaw parrots sharing a milkshake with 2 straws. So this is not a prompt that can be processed just like that, because it contains multiple objects, and you got to be a little careful in your AI modeling world to deal with this kind of stuff. So we are saying 2 macaw parrots, that's 2 objects already, sharing a milkshake, which is a third, with 2 straws. So 5 objects in total. They have to be each rendered correctly, and then they all have to be placed in the right location. So this is going back to that multi-stage, pre-production, production, post-production kind of ways of thinking, that if you really have to get this right, Well, you have to generate each of these 5 assets separately first, and then place them in the scene and connect them in the right way. That's the way to think about it. But once again, you can take the text prompt as is and pass it to any of the existing 3D generative models out there, and they'll do a job which is not very satisfactory and will show you results because they're trying to do it one shot. Take the text prompt and get the full output out, and they mess things up. So we are trying to break it into these stages of one asset at a time, then think of the layout, then make the connections and refine everything. So that is what we are trying to do. Once again, giving more control and aligning the AI modeling process to how a 3D asset creation pipeline might actually work, which is through stages. I will skip some of the details, but again, the high-level idea is we start from the text prompt. We use GenAI models. More technically, these are called vision language models because you're producing a visual output from a language input, so VLMs is the keyword that goes with it. We process the text prompt to get what is called a scene graph, which basically is a abstraction of this sentence into concepts and their connections. So the scene graph might look like this. So this bottom part that you're seeing is a scene graph representation of that sentence. 2 makeup Harrods sharing a milkshake with 2 straws. So these are all concepts. So each object is a node, and then what they're doing, the verbs get attached to the nodes, and then also layout can be attached behind, in front of, to the side of. All that knowledge can be expressed in graphical form. So we use the scene graph, which is, by the way, generated through language modeling, VLMs. We also take a simple 2D rendering first, because remember, as I said, 2D image generators are way more robust than 3D. So we also pass the text prompt to a 2D generator to just get a reference picture saying, oh, this is what it should kind of look like. So take that reference picture, take the scene graph, and then start processing the 3D side of it and try and align the 3D world to the 2D when you render it back to 2D. So try and use the 2D as a weak constraint and then keep refining everything. So here are some examples. So a wizard standing in front of a wooden desk, gazing into a crystal ball placed on the wooden desk with a stack of ancient spell books sitting on the wooden desk, and next to the crystal ball is the input prompt. It's a very complex prompt. There's 4 objects, right? Or, if you consider a wizard as an object, there's 4 models, let's say. There is a wizard, a crystal ball, a spell book, a table, and there's all kinds of things in the text prompt about what's in front of what's on top of what. So all that has to be expressed through a scene graph, and we process that through our 3D generator, and this is the output that we're getting. This might look like interesting and reasonably fine. It might look a little cartoonish, and there are reasons why all that's true. The cartoonish feel comes because most of the 3D training models that we have, the training data sets we have, tend to be cartoonish already. So there is a bias in the 3D training data sets towards making pictures like this, but we're able to get the layout fine. Now, as a comparison, here are comparisons, like are we doing better than anything out there? So again, 2 different comparisons, 2 different text prompts. A well-furnished bedroom with a Baroque-style bed, red pillow on it. You can read the whole thing. In the middle section, we have 4 different standard 3D GenAI models that have processed this text prompt. You have to really read the text prompt in its entirety and check whether everything in the text prompt was rendered or not. Our understanding is most of them did not get everything right. And the final column shows what we are able to do. So because we break the text prompt into individual objects, a scene graph, we are almost guaranteed to generate at least every object that is in the scene graph. And then there is the layout aspect to it. So this is how we're advancing the field, and I think some of these things will start making their way into more popular applications like game engines, and some of these things, if done right and if placed on a web backend, can become a simple web interface for artists to play with. Another example, knight in shining armor gallops on a brown horse, wearing a blue hat, holding a sword in his right hand. Princess sits beside him on the same horse, wearing a flowing gown and a jeweled crown. Very complex prompt. Standard models are messing it up. Some don't even get the princess. This is pretty funny. I don't even know what's going on there. And this is our model. To me, this is looking it is very well aligned with the text prompt. You may not like the visual quality of the look. It might be not the look you're going for, but at least the geometric layout, the topology, the shapes are all correctly rendered. The visual style of it, the colors, the textures, the lighting, we call that style. We are not necessarily optimizing for all that. Right now, our work is more on optimizing the underlying shape and geometry and topology. So from that perspective, it's doing well. If you take this idea forward, that the types of models we are building are giving more control to artists and aligning 3D content creation with the pipelines that artists generally seem to understand as the right way to do it, which is make the assets first, sketch it out roughly first, which is what we're doing by asking the AI model to give us a 2D picture first. That's what we would call pre-visualization. And then the actual asset creation, the 3D stuff, then put it all together, use the pre-visualization as a guidance, but don't have to be limited to it, but at least it's there to guide you along the way. So that's how we are thinking about modeling. And if it takes off, if this actually becomes a product, we estimate that there's going to be enormous amounts of time saved for 3D experts. We are sensitive to this debate of whether we are replacing 3D artists or we are helping them. The way we are thinking of the models, because there is such a required input from the artist in either a high quality 3D model or something that allows them to at least edit the scene graph if it's not correct, there is some degree of control the artists have in how this gets used. So, but this amplifies their work, and it definitely helps them create variation to something they may have made with painstaking detail, but it helps them reduce their time in making variations on that. And the reductions are enormous. These are estimates from just a literature survey and talking to 3D modeling artists. Making a basic layout with multiple objects takes 3 to 6 hours. Complex environments takes days, and then just making the whole thing high quality is also something that takes days. With AI models, it can happen in a matter of hours. So there is certainly a way in which artists may benefit by the oncoming onslaught of AI. But in order to be able to do that, they can't be just passive users of the AI models that get thrown at them. They have to be in the mix at the modeling stage and work with the computer scientists, work with the AI modelers, and inform to us things like the architecture. What is the input that should come from the artist, and what is the part that AI should take over? So those discussions have to happen at the very front end, and we do that in my lab, the Geometric Media Lab. And if it's done well, if it's done in a harmonious way, we believe that artists stand to benefit. There may be different business models that may have to come about. For example, this is a little slide we made for a pitch deck for some of the projects we are doing. And the way we were thinking about it is if it takes 5 days of work for an artist to make one asset or one scene for a client, and they charge X number of dollars for that. So if we give these tools to them, it just means they are able to do more projects, but then they have to be able to tap in to more clients in a way. And it can certainly lead to more productivity, higher levels of income, or maybe the same amounts of income in less time, so their time frees up to do other things. So all of these things are possible with what's happening with AI, but artists have to be in the mix to enable this to happen. We can't surmise from our side what artists really want, and artists have to engage with us. So with that, I would start closing out. Some of the work we are doing is protected by IP. We have invention disclosure. Some of our funding does come from the National Science Foundation and DARPA, DoD funded. But we're finding that many of the things we do have dual uses. High quality, controllable generative AI is high interest to not just the games community or the 3D community, but also to the DoD. These are all dual applications that we pursue. We've had invention disclosures, which are in different stages of being patented, and several publications that reveal what we are doing. I encourage you all to study them if you have time. And with that, I would say thank you for listening, and I'm happy to answer questions. If you have any, please shoot me an email, and I'll be looking forward to hearing from you. Appreciate it. Thank you.